Hello, my name is Christopher Ellis, and I'm a PhD student and member of SecLab at The Ohio State University, advised by Professor Ji-Chiang Lin. I'm grateful and honored to present our research to you all today, titled Replay Far Away, Exploiting and Fixing Google Apple Exposure Notification Contact Tracing. I'd like to thank my co-authors, Hao-Hyung Wen, Professor Ji-Chiang Lin, and Professor Anish Arora. Also, thank you to the PETS chairs and organizers for this year's symposium. In this presentation, I'll be introducing our enhancement to the Google Apple Exposure Notification Framework, which adds geospatial awareness to defend against geographically distributed crowdsourced replay attacks. So first, a bit of background on contact tracing and motivation for our research. Digital contact tracing aims to be a scalable solution beyond manual human contact tracing. It is often implemented as applications for smartphones that leverage both new and existing protocols. The three high-level functions of contact tracing aim to determine encounters with others, whether or not it is epidemiologically significant, and to communicate the encounter, particularly if someone tests positive. These functions can be effectively characterized by centralized or decentralized approaches, though most are some sort of hybrid that balance a trade-off between data utility and data privacy. And now to briefly introduce Google Apple Exposure Notification Framework, or GAIN. GAIN is a joint effort between Google and Apple that is heavily based on DP3T, one of the many protocols introduced relatively early on in the COVID-19 pandemic. This is a largely decentralized protocol in the sense that it is effectively using Bluetooth Low Energy beacons to determine encounters, algorithms at the edge or on the smartphone to determine significance, and effectively a bent pipe public health authority server to distribute anonymous data. It is open source with reference implementations available on GitHub. Effectively, approved public health authorities must develop apps that utilize the exposure notification software development kit to take advantage of lower-level operating system functionality. The high-level concept of GAIN is as follows. Smartphones generate daily pseudo-random keys, known as temporary exposure keys or TEKs. Then roughly every 10 minutes, drive an ephemeral token to broadcast known as a Rolling Proximity Identifier, or RPI. These RPIs are then broadcasted and captured over Bluetooth Low Energy. Upon a positive diagnosis, users can elect to anonymously upload their pseudo-random keys to a public health authority server. Other users' smartphones will periodically receive these anonymous keys and use them to derive tokens to match with those they've already captured. If there's a match and it meets an encounter threshold with time and RSSI, the user is notified of a potential exposure. Here's a look at the typical GAIN scenario. At 1, Alice broadcasts her RPIs. Nearby and within BLE range, at 2, Bob captures and stores them. Out of range at 3, Charlie does not. Unfortunately, Alice is later diagnosed positive and elects to send her anonymous TEKs to the Public Health Authority server. These keys are combined with other positive case keys and periodically distributed to all subscribers, including Bob and Charlie. Both Bob and Charlie's phone will derive RPIs from the TEKs, but only Bob's will determine a match with an RPI captured from Alice, prompting a notification. Whereas Charlie will not match because she never captured Alice's RPI to begin with, not ever being within BLE range. The existing GAIN framework is vulnerable to replay attacks because it only considers time for RPI validity, and therefore lacks geospatial awareness of where the RPI was actually captured. As such, and as an example, an RPI is equally valid in Columbus, Ohio, as it is in Brooklyn, New York, hundreds of miles away. This is illustrated in the following workflow where in Columbus, Ohio, at the Ohio State University Library, Alice once again broadcasts her RPI, but now both nearby Bob and malicious actor Mallory capture it. Mallory transmits the RPI to a replay attack server, which then immediately distributes it to other malicious actors, such as Malachi in Brooklyn, New York. Malachi broadcasts the RPI at a hip local coffee shop, and nearby Charlie captures it. When Alice is later positively diagnosed and elects to upload her TEK, Bob will rightfully match an RPI, but so will Charlie, even though she was never near Alice. With an introductory background, we can now move on to our research and contribution. The geographically distributed replay attack and other related works motivated 3 distinct research goals in the development of our solution, GAIN+. The first, to retrieve user locations without compromising user privacy. Then, use this data to enhance GAIN with geospatial awareness to defend against the distributed replay attack. And finally, to incorporate these enhancements with minimal rework and to preserve the essence of the protocol. Otherwise, we'd really just be creating a whole new solution. We accomplished our first goal by utilizing Wi-Fi and cellular positioning that are provided by course location services on smartphones. This offers significantly reduced power consumption over a more precise GPS query. And further, it does not violate GAIN's additional terms that prohibits using precise locations. The second goal is achieved through the use of hierarchical geospatial indexes, which effectively provide a grid overlay for the entire Earth. Rather than use political boundaries like city, state, or county lines, a grid overlay provides an agnostic, uniform, and efficient way to determine location. Fortunately, there are many open source solutions already available with trade-offs and various approaches to defining the parent-child hierarchical structure. On the left, we have GeoHash, which uses Z-curves. In the middle, Google's own S2 library using geodesic squares, and Uber's H3 library using hexagons on the right. Each are shown here with some parent level or resolution n in solid lines, and resolution n+1 in dashes. We chose H3 for its more uniform overlay and the reduction in neighboring cell calculations, which I'll return to shortly. And finally, our third goal enhances GAIN with minimal rework and leaves the algorithms largely intact. I introduced TEKs and RPIs earlier, but there's a third key that is derived between these two called the RPIK, or Rolling Proximity Identifier key. The RPIK is the 16-byte result of an HMAC-based key derivation function, or HKDF, which takes the daily TEK and some null bytes and a constant string. The null bytes provide a natural place for the location index provided by H3. Further, when a user captures a nearby RPI, the H3 library is queried for a location index and securely stored to later use to derive and match RPIs. This modification is perhaps more clearly illustrated here, where we can see the new location-based RPIK derivation provides location context with bi-layer indirection. In other words, both the TEK and RPI are generated and transmitted as before with the original GAIN framework. However, neither contain complete information to derive location. We implemented GAIN Plus on Android using the reference source code on GitHub provided by Google. Effectively, we enable course locations, include the H3C library, and use the H3 index as the salt value to derive the RPIKs for both RPI generation and matching. And now for our evaluation of our prototype. We measured the effectiveness against geographically distributed replay attacks. In this experiment, we created 9 user activity and user density profile combinations. Here we are looking at densities of 100, 200, and 400 users who elect to upload their TEKs upon a positive diagnosis, resulting in over 200,000, 400,000, and 800,000 RPIs generated and broadcasted over 14 days, respectively. They are randomly placed throughout 50 locations. Then, we model a victim user with a low activity profile who visits 5 out of the 50 locations throughout this period, but captures 3% of the total RPIs broadcasted. We observe that GAIN inaccurately matches 100% of the captured RPIs, even though the victim user only visited 5 out of the 50, or 10% of the locations. Also, that GAIN Plus accurately matches approximately 10%. This difference effectively gives a false positive rate of the original GAIN, showing approximately 90% RPIs matched from locations the victim user had not actually been present. Next, we evaluate the impact of the resolution parameter using our non-uniform distribution location dataset. Starting on the left, we can see Brooklyn, New York is almost entirely captured in a single cell at resolution 4. At resolution 6, we now see about 6 cells, and then even more at resolution 7. We now use a medium user and medium activity profile that generates over 400,000 RPIs, again with the victim user capturing 3%. At resolution 4 through 6, GAIN Plus performs like GAIN because the resolution produces relatively large cells for this particular movement profile. At resolutions 10 and 11, we observe the number of matched RPIs converges to 1,454, as well as the number of cells required to contain all potential visitor locations and the time required for matching computation. While this represents approximately 12% of the roughly 12,000 RPIs captured, we note again the non-uniformity of our Brooklyn, New York dataset. We then evaluated GainPlus for its power consumption. On the left, we evaluated RPI derivation, updating location every 60 seconds for 2 hours, and see the difference throughout is roughly 1%. In the middle, throughout 10 minutes of RPI matching, GainPlus is again within 1% of gain and actually performs better, likely due to the original gain making more JNI calls. On the right, we see for an equal-sized set of TEKs, GainPlus continues matching as expected, requiring approximately 9% more battery. We compared GainPlus to related works and observe it hits the marks for adding a location context without modifying or directly including location in the payload and without additional third-party apps for infrastructure or uploads to the Public Health Authority server. We'll now close with discussion and future work opportunities. We utilize the hierarchical characteristic of H3 to handle the case where two individuals are near each other across cell boundaries and for any fuzziness in coarse location. We use a resolution R to provide location context for the L-RPIK, but we use resolution R+1 to store location for later RPI matching. When it comes time to match RPIs, for each R+1 location in blue, we retrieve neighboring cells and check its parent. If it's the same parent, continue. If it's different, add the parent to the set of additional location cells to use for RPI derivation. This reduces the total number of neighboring cells in the naive approach from 6 down to 2 or 0 in the case you're located in the center of a cell. We observe that GainPlus is effective at defending against geographically distributed replay attacks. RPIs can still be replayed within the same cell they are captured. The resolution can be tuned, however, with performance trade-offs. We also observed location precision is different across platforms. As a solution, Google and Apple can provide a uniform option accessible only by GainPlus. And finally, an opportunity for future research for dynamic resolutions that adapt to user densities. Thank you again for the opportunity to present our research.